All right, so thanks for coming. So this is a big room. The other room was taken today. It's a big room for not so many people, but few, but good, very, very well. So I have the pleasure to host David Nesvorný again for his third talk, and next week will be the last. So today, David shifts from the outer solar system into the inner solar system, an asteroid belt. And he's talking about the collisional evolution in the asteroid belt, the formation of asteroid families. David is the person who identifies all these families. His catalog of families is the reference in the whole community. And the link between asteroid families and meteorites. And then next week, he will speak about big meteorites, which are near-Earth objects and collision probability with the planet and so on. So, David, please.
Thanks, Morby. Thank you for coming. Good morning. So this is the asteroid belt. There are about 1.5 million asteroids currently known. They range in sizes between several hundred meters to the biggest, Ceres, which is almost 1,000 kilometers across. Very roughly, it's estimated that about 1 million of these bodies are larger than 1 kilometer. This gives you the sense of how big this population is. The thing that's relevant for today is that the asteroid orbits are crossing each other, and therefore there's potential for collisions between them. There's also lots of empty space, so the collisions do not happen too often. But if you have 4.6 billion years, then many will happen. There are two kinds of collisions, roughly speaking. It could be a cratering collision or a disruptive collision. So we have plenty of evidence for cratering collisions, right? This is an example of a heavily cratered surface of asteroid Ceres. It was imaged by the Dawn spacecraft. The fact that there are so many craters immediately tells you that the surface is very old. So this is for relatively small impactors impacting a very, very large body, but occasionally in the asteroid belt you have the opposite situation, where you have a relatively large impactor impacting a relatively small target body. And in that case, you can have disruptive collisions, in which the parent body is broken in pieces, and these pieces are ejected into space. Now, many of these pieces will be tiny, will be dust particles, will be meteorite size, but some of them at least can be kilometers in size, and they can be detected by telescopic observations. So we call these collisional families or asteroid families. These are collections of the fragments produced in disruptive impacts. We don't have images of disruptive impacts, but we have simulations, computer simulations, and this is one of the simulations I worked on. This is a situation 15 seconds after the impact. In this specific case, that was modeled after one of the families in the main belt. There is a 35-kilometer target asteroid that's impacted by a 5-kilometer impactor at 45-degree angle. The impact velocity in this case is 5 kilometers per second, which is typical what you get in the asteroid collisions. And if I run this, you can see the survivor body, the largest body that survived this collision. In this case, it's about 70 kilometers across, representing something like 15% of the parent body mass. So this is a catastrophic impact. If the largest fragment represents 15% of the parent body mass, it means that 85% of materials is ejected into space in form of large, smaller, and smallest fragments. So this is what we would see if you look at the same collision from far. You would see all these fragments being ejected. The interesting thing about this is even though the impact speed is about 5 kilometers per second, which is relatively high impact speed, the ejection velocity of the fragments is only of the order of tens of meters per second. And that will be significant for identification of the asteroid families. This means that the ejection speed is tiny compared to the orbital speed, right? So, which means that the fragments initially will not be only at the same place, at the site of the collision, but after the collision, they will also have a very similar orbit to each other, because the delta V is just a small perturbation of the orbital speed. So all the fragments will essentially continue on the same orbit. So because of many of these families happen, many of these collisions happen many millions of years, billions of years ago, we have to consider how the fragments evolve on long time scales. If you would like to identify a family that's 1 billion years old, we need to know how the fragments evolved to understand how we can identify and link them to the same impact. So let's first consider the shortest time scales. So this is a fictional breakup. So you have the inner planets in the middle and the site of the breakup here. I created something like 1,000 fragments there, give them 10 meters per second, so they are at the same place originally. And this is what happens on a relatively short time scale. You have time here running in kilo years, so this is about 30, 40 years after the impact. So what happens here is that although all the fragments have almost the same orbit, some will have slightly lower semi-major axis, some of them will have slightly larger semi-major axis, and because of the semi-major axis links to the orbital period, some of the fragments will be orbiting faster and some will be going slower, which produces this shear where the initial concentration of the fragments essentially spreads over all the orbit, which corresponds to the parent body orbit before the impact. So what this means for identification of the fragments from the same breakup. This means that even if the breakup happened only hundreds of years ago, the fragments will want to be in the same place, right? You can't look at some direction in the sky and see all the fragments there. No, they will be spread all over the orbit. But at the same time, this provides means how to identify these fragments. Because if you have a catalog of 1.5 million asteroids, you can perhaps search for bodies that have about the same orbit in 5 orbital elements, and then establish the statistical significance of it, and maybe you can convince yourself that's a real family. Before we do that, let's make things a little bit more quantitative. So I just remind you briefly what the orbital elements are. Semi-major axis is basically the size of the orbit. Eccentricity is the elongation area of the orbit. Main belt asteroids have eccentricities ranging between 0 and 0.2, between 0 and 20%. Inclination tells you the tilt of the asteroid orbit with respect to the solar system plane, which we also call ecliptic. Asteroids have typical inclinations between 0 and 20 degrees. And in addition to these 3 orbital elements, you have also 3 orbital angles. The true anomaly F is this angle here, is the angle between pericenter and the asteroid position on the orbit. Then you have the argument of pericenter. Argument of pericenter is the angle between the longitude of the ascending node and the pericenter. It tells you how the orbit is rotated within its orbital plane. And the last angle is the nodal longitude. If you have some reference direction in the ecliptic, that's the angle between that direction and the longitude and in the ascending node. Ascending node is where the orbit goes above the ecliptic, right? So these 6 elements together define the orbit and the position of the body on the orbit. It's a full set that uniquely defines the situation. So coming back to this, this means that if you go to Minor Planet Center, you download this huge catalog of orbits, you have 6 orbital elements for each asteroid. What you expect for fragments produced by a collision only hundreds of years ago is that they will have random true anomaly. They will be spread all around the orbit, but they will have clustered semi-major axis, eccentricity, inclination, longitude of node, and the argument of perihelion. They will be significant clusters in these 5 elements. And this is an example of it. This is a small family around asteroid 9332. This is a table that shows the bodies that are clustered to this object. You can see that there is a very tight clustering in semi-major axis eccentricity inclination, but also if you look at the orbital angles, I think the most fascinating is the longitude of node, where the clustering is of the order of 0.1 degree, right? So this is how it looks like in the projection of nodal longitude, at perihelion longitude. It's very, very tightly clustered. You can ask the question, how statistically significant is this? How frequently you get this by just random fluctuation of the orbits in the orbital space? And the answer is 0. This is significant to many dozens of sigma. So this is a real family. If you study it more detail, you can even estimate the age. And in this case, this breakup happened only 16 to 17,000 years ago. It's actually the current record holder for the youngest family, youngest breakup that has been identified so far. Okay, so now this was just like a time scale of hundreds of years. It's unlikely that the breakup will happen on hundreds of years. It's more likely it happened millions of years ago. So let's consider the evolution of the fragments on a longer time scale. So let's reset the time. Let's run a little bit faster so that we cover at least several millions of years. So now what happens is that the fragments that share the same orbit, they start precessing at different speeds, right? They have slightly different semi-major axes, and because of the precession of the orbit is a function of the semi-major axis, then some fragments precess faster, some precess slower, and this creates this slinky effect that I call a slinky effect because of it resembles just like wires that are twisted in space. So this is bad news, right? Because of now, if you consider collisions happening millions of years ago, you know that the fragments shouldn't be on the same orbit. So you don't expect tight clustering in all 5 orbital elements. This is how the slinky effect looks like when you plot the pericentral argument with respect to time. This is the time of the breakup. At the time of the breakup, all the fragments are at the same, have the same longitude, have the same pericentral longitude, and then over time they decorrelate. Here actually what's plotted is the relative pericentral argument, relative to usually the largest fragment or some reference, because of otherwise the precession would be too fast and you wouldn't see too much. So this is a relative pericentral argument, and you see the decorrelation of the fragments. So if the family is a few million years old, you don't expect any clustering. And the same thing happens in the longitude of node, because of the nodal precession also depends on the semi-major axis, and you get this decorrelation. So now what, right? You have this effect. Is it useful to something? And it actually is useful to something because of, think about the following, right? Maybe you identified maybe some cluster in the inner belt. Maybe you suspect that this is a relatively young family, right? Maybe the bodies in the family have similar spectroscopic properties. They look like the fragments from the same body. Then you can try the following. You can take their oscillating orbits at the time of at the present time and integrate them backwards in time, trying to find some convergence of the angles, right? And if the statistically significant convergence happens, then you suspect that the breakup happened at that time. And this has been done many times in the past. We have dozens of these cases. I think the latest count was that we have 100 these cases. And this is just 4 examples from these backward integrations. So these are 4 families, Jones, Rampo, and these 2. What you do is the backward integrations from time 0. You get all the fragments coming back, processing at different rates. But sometimes you get convergence just in the nodal longitude, not in the perihelion longitude, although there might be some convergence. But in many cases, you get clear convergence and simultaneous convergence in both angles, which is clearly significant. And you conclude that, you know, Jones family is about 2.5 million years old. So this is significant for at least 2 reasons. First of all, you prove that these fragments are coming from the same collision. You prove it. And the second one is that you know the age of the family and many families. And this is useful if you study things like space weathering. You want to understand how fast the asteroid surface is changing in time. So it is useful to know the surface ages of the families. And in fact, all these bodies in this family will have the same surface age, about 2.5 million years. So you can look into how you know, the spectrum is different from maybe older surfaces, younger surfaces, and understand that space weathering, for example, proceeds relatively fast, and within 1 million year, you already have space weathered surface. This is an example of the distribution of ages of the young families, where this method of backward simulation works well. So what's shown here is the family age on the x-axis, and the largest member absolute magnitude on the y-axis. The red symbols were previously known families. The blue symbols are the new ones that have been discovered this year. With the LSST coming on, this plot will change within a few years, and there will be, you know, dozens to hundreds of new cases here. So what happens here is that the size of the symbol is proportional to the number of family members we know in that individual family. So for example, for this family, we know about 2,000 members. For some of the small families, we know only a dozen. That was the case I showed one of the first slides. So this distribution makes sense, right? If you consider just last million of years, you get lots of these convergent cases. If you go a little bit back in the past, you have none of them. And it's basically because of this method works only if the family is young. If the family is somewhat older, you can't recover that convergence because of there are additional perturbations like encounter with series and also radiation effect that just doesn't allow you to go too far in the past with this distribution. But this data set is useful for issues of space weathering and also understanding the collision evolution of the asteroid belt. People who study collisional evolution of the asteroid belt try to understand which asteroids are primordial, which are fragments, try to understand the size distribution evolution and other things. This data set is useful for them because they need to reproduce this number of families in the last million year. Okay, so so far we talked only or mainly about the 3 angles, right? The true anomaly, mean perihelion longitude, and nodal longitude. But let's now consider what happens to the semi-major axis eccentricity inclination, how they evolve on long time scales. So one thing that's very useful are the Gauss equations. The Gauss equations, they relate the ejection velocities of individual fragments to their new orbits. So the velocity vector has 3 components: tangential, radial, and vertical. These are the ejection velocities. I said that the order of magnitude, this is tens of meters per second. And well, Gauss equations relate these quantities, which appear here, in linear fashion. They map them into change in the semi-major axis, change the eccentricity, and change the inclination, where the change is relative to the parent body before the breakup. So these equations allow you to calculate the change. The interesting thing is, well, these coefficients, they depend on the eccentricity and semi-major axis of the parent body, but also on the true anomaly. So the true anomaly is here. So these two first equations depend only on the true anomaly. And this last one depends on the true anomaly plus the argument of perihelion. So this mapping from the velocity space to the orbital space will always depend on these two quantities. How this look like in a plot? So this is a breakup. I've chosen the breakup somewhere in the middle asteroid belt, some low eccentricity, low inclination. The velocity field was assumed to be, up to 15 meters per second. And then I mapped using Gauss equations the velocity field, assuming it's an isotropic ejection velocity field, which is a pretty good assumption, into the change of the orbital elements. So this is the dependence on the true anomaly. If the breakup happens close to the perihelion of the parent body, so the true anomaly is, for example, 30 degrees, then you find that all the fragments will be located within this ellipse. So there will be a correlation, direct correlation between semi-major axis eccentricity. If the breakup, on the other hand, happens in the aphelion of the parent body, then you will find from Gauss equations that the semi-major axis and eccentricity should be anticorrelated. And, the cases in between. So, for example, for 30, you expect the fragments to be located in this ellipse. Now, the dependence on the true anomaly and the argument of pericenter that influences the mapping into the inclination distribution of the fragments. Now, if this angle is 0, that means that the breakup happens in the ascending node of the orbit, because of f plus omega is the distance from the ascending node. So if the breakup happens in the ascending node, there is a potential for relatively large change of the inclination. But if the breakup happens 90 degrees from the ascending node, so well above the ecliptic, then the expected change in inclination is 0. So somewhere in between, for 45 degrees, you expect the breakups to be located in this specific ellipse. To give you a real-world example for this is a small collisional family. And you can see the blue ones are the fragments that were identified in the family, in eccentricity space, in inclination space. And you can fit an ellipse to these distribution, and this ellipse is about 8 meters per second, so the ejection speed even lower than in the previous case. And you can see this clear correlation between the eccentricity and semi-major axis, which tells you that the breakup happened somewhere 60 degrees from the perihelion. And for this specific family, the method of backward integration works, and you can establish that it's 3 million years old. So the lesson we learned here is that the Gauss equations work, and they are clear example of this in the main belt. Okay, so what happens on even longer time scales? We discussed the time scales of several hundreds years, then we go to millions of years, but let's now consider tens of millions or hundreds of millions of years. So I have, to illustrate that, I have created this fictional family. In the inner main belt, I assume that the breakup happens with these conditions. This is the ellipse corresponding to that, and there are like 100 fragments located in the breakup. So let's see what happens to the orbital elements if you consider timescales of tens of millions of years. This is what happens. Because of there are planets that are acting on this population, there are all sorts of oscillations that start with different frequencies. Some some mainly produced by Jupiter, but other planets contribute as well. So if you wait only 10 million years, you have a dispersed cloud in the orbital elements, which still, looking at this, you could identify this family, but the problem is when you consider the background, and there are many background asteroids, then it becomes much more difficult to identify the family. And this is what happens only after 10 million years. If you look at this, it's very difficult to understand whether there was a breakup or not, right? So this highlights the difficulty of identifying the families in oscillating elements if timescales of the order of 10 million or longer are involved. So what do we do about it? And there is a classical method in celestial mechanics that works for it, which is defining constant of motion, which are called the proper orbital elements. So what you can do is that you combine the eccentricity and the longitude of perihelion into a complex variable just to have compact expressions. I didn't want to write too many equations, so I just used this variable. And then you basically know that this variable will have oscillatory changes, and under some assumptions, the evolution can be written as a combination of several elements. The first one is the oscillation or circulation on a frequency g, which is called the proper frequency of the motion, and will have certain amplitude, which is denoted as proper eccentricity, plus the terms forced by the planets. The planets have their own frequencies, and depending on which planet it is and the semi-major axis of the asteroid, these terms will have some forced amplitudes. And all this combines to produce lots of different oscillation in the orbit that we have seen in that previous animation. Fortunately for us, there are both analytical methods and numerical methods which allow us to cancel this from the expression. So for example, what you can do numerically is to do a numerical simulation over a few million years. You know what frequencies you expect there. You expect the planetary frequencies, you know what planetary frequencies are, and you expect at least one frequency which is proper frequency of the asteroid. So you do a Fourier analysis on it, and you remove all the oscillatory terms from the evolution that contain the planetary frequencies, ending up with just simple evolution where this AP is a constant of motion. It doesn't change. It doesn't matter if the breakup happened 10 million years, 100 million years, 1 billion years ago, that AP will be always the same. And you can do the same for the inclination and the semi-major axis. So this is the basis of the definition of the proper elements. So coming back to this is just after the breakup. This is 10 million years later, but I took this and applied the proper element calculation for that, and if you do that, you recover the original family. So that's the beauty of the proper elements. These are constant of motions. They are related to the orbital elements, but unlike the orbital elements, they don't change with time. And therefore, they can help you to identify families that are even billions of years old. So this was just a small example, fictitious example, but you can automate that technique and calculate the proper elements for all 1.5 million asteroids in the main belt. And this was done here. This is just the orbital distribution when you download things from the minor planet center and you plot the oscillating elements. And this is when you process this distribution, you calculate the proper elements, and you replot 1.5 million asteroids. So what you can see here that, well, sometimes there are hints of some concentration. But with the calculation of the proper elements, these concentrations become much more clearly defined. And here you don't see much, but here you see lots of structure, maybe dozens of clusters, and all these are actually collisional families. So when you do that, then you have to apply some clustering method to understand how many families you have, what are the memberships of each family, whether the families are statistically significant. Of course, you recover all the known classical families that go all the way to Hirayama in I believe, 1980s, in 1918. The families are called after their largest member, usually. So in many cases, like the Themis, it's pretty clear that the Themis is the largest member. In some cases, there are two asteroids that are about the same size, and one has to be careful about not changing the names of the families. But these are the classical families that you recover. But you can do better than that. And this was the effort we worked on this year. We basically identified all the previously 122 known families, but added about 240 to them, basically tripling the sample for the total of 360 families. So these are some of the examples of the identification method. This is a cut through the middle belt between 2.5 and 2.82 AU. You have the proper eccentricity, proper inclination, and you have all these clusters, and all the circles identify a family that was identified here. The red ones are the old families, the blue ones are the newly identified families, and the same for the outer belt. So by applying this technique, you basically recover hundreds of collisional breakups in the main belt. And again, this is a useful constraint on collisional modeling. Because of these breakups uncover the asteroid interior, it also informs you about asteroid differentiation or lack of the differentiation in this case, and many other issues. I would like to focus on the radiation effects, and for that I will consider one of the very interesting families, which is the family around asteroid 832 Karin, and this is the one. This family was discovered 20 years ago and now has about 2,000 bodies there. So let's look into this family in a little bit more detail. So this plot comes from the original discovery paper, where there were only several dozens of asteroids known in the family. As I said, now we have more than 2,000. The first of all, you see that the Gauss ellipse here is pretty inclined, indicating that the breakup happened close to the perihelion. And this is the distribution in the inclination. The blue ones were identified as the family members. The yellow ones is just the background. The impact modeling I showed at the beginning of this talk actually was tailored to the Karin family. That, if you remember that setup with the 35-kilometer target asteroid and 5-kilometer impactor was exactly the modeling of the Karin family. The 17-kilometer survivor body is actually 832 Karin, and many features of this distribution are reproduced. Maybe the impact modeling is indicating a much tighter correlation between the eccentricity semi-major axis. But as I will show, this is due to the small drifts these bodies had over the past millions of years in semi-major axis due to the radiation effects. So when you track the orbits of the Karin family backwards in time, you start here at time 0. You collect all the members, and you track them backwards. You see this beautiful convergence about 5.7 million years ago, which tells you that the Karin family formed 5.7 million years ago. So it's one of the young families, not the youngest, but one of the young families. What is interesting on this is the following. The convergence is pretty good, right? But if you look at the spread here, it's about 60 degrees here and maybe 80, 100 degrees here. So what's happening here, right? If the bodies were produced by the same breakup, the concentration of or clustering of both angles at the time of the breakup should have been of the order of 1 degree. That's what the Gauss equation tells you. That's what were the examples I was showing. But here, it's much less tight clustering. So what's happening? Are we missing some element in this? Maybe there's some external perturbation that we didn't take into account by this integration. By the way, this integration backwards just accounts for the effects of the planets. There's nothing else, just gravity of the planets. So what happens here is that there are additional effects that change asteroid orbits, and one of them is the thermal Yarkovsky effect. Let's look at this figure. This is an example of a body that has prograde rotation. So prograde means that the rotation is in the same sense as the orbital rotation. That body is heated on one side by solar irradiation. So this side is heated, and the body rotates, and there is a delay in re-emission. Just like on the Earth, when you have, the hottest is at 2 o'clock, not at midday, then there's always some delay in re-emission of the absorbed radiation. So in fact, it turns out that the body rotates, and most of the thermal photons escape in this way, and they act like a small jet on the body, which slightly accelerates the motion. And when it slightly accelerates the motion, means that the semi-major axis will be drifting out. The orbit will be slowly expanding. This effect is small, depends on the size. It is insignificant for 100-kilometer bodies, but very significant for kilometer size or even smaller bodies, right? And so this is the extreme case where the spin axis was perpendicular and the orbital and the spin motion was prograde. In the opposite case, where you have an asteroid that has spin pointing towards the south pole of the orbit, you have the opposite happening. Body gets heated, rotates, re-emits thermal photons in this direction, which is the direction of the motion. So it's pushed this way, slows down, and the semi-major axis drifts towards the sun. So in these two extreme cases, you have increasing semi-major axis, decreasing semi-major axis, but you can imagine also the cases in between when the spin axis is not exactly perpendicular to the orbit, but it's tilted, and in those cases, it will be something intermediate between these two cases, right? So the significance of this is that when we are integrating the current family backwards, we didn't account for this effect. But if this effect is real, then the members of the family should be slowly drifting in semi-major axis. And as they drift, the precession speed would change because of the precession speed depends on the semi-major axis. So it is possible to account for that. We don't know the orientation of the obliquities in the family, but we can turn the question. We say, let's assume that the asteroids drift. What kind of drifts you would need to produce a perfect convergence? Infer the drifts instead, and from drifts you infer the obliquities. Let's turn it around, right? So this is what we have done here. So this was the situation without accounting for the Yarkovsky effect. And when we accounted for the possibility of small drifts, then this happens. It improves enormously. What happens is that these trajectories are not straight. It's difficult to see, but they are not straight lines. Because of the asteroid is drifting, the precession is mean. They bend a little bit and then bend in such a way that they don't overshoot. They just bend into the convergence. Now, this is not 1 degree, but we later realized that there are additional effects, like encounters of these members with large asteroids, like Ceres. These encounters produce stochastic effects that are difficult to account for, and they lead to this imperfect convergence. But still, from this exercise, what we derive is we found what the inferred semi-major axis drifts are for the family. We divided by the age of the family, so we have basically dA, dt for all the bodies in the family. And this is the distribution of the of the drift rates as a function of the asteroid size. We know what the albedo is, so this ranges, from 0.5 kilometer to 5 kilometers, and you have the distribution. So is these inferred drifts consistent with the Yarkovsky effect? From theory, we know that for reasonable parameters, the maximum negative drift for a body that has retrograde rotation should be here. So this is the envelope. We don't expect any drifts on the left from it, and the maximum positive drift for a prograde body perfectly has a spin axis perfectly perpendicular to the orbital plane should be here. So the distribution of these points is perfectly within these envelopes, which tells you, well, this is really consistent. What we are measuring here, in a sense, is really the Yarkovsky drift. Now, as I said, the Yarkovsky drift depends on the asteroid obliquity, which is the angle between the spin vector and the orbit normal. When you have the breakup and the pieces of the breakup fly into space, you expect that the distribution of obliquities should be random, right? There's no reason for the fragments to rotate in the same way. And if you look in this place for the large objects, it is kind of random, right? You convince yourself it is random. So that's consistent. The problem is, when you look here, you see it's not random. There is a gap in the middle and higher concentrations on the sides. So what is happening for these small guys? They apparently don't have a uniform distribution of obliquities for some reason. Okay, we looked into that in more detail and realized we are still missing additional effects. The additional effect we are missing is the YORP effect. The YORP effect is like the Yarkovsky effect, but instead of the radiation force affecting the orbit, it affects the obliquity and the spin state of the body. So the YORP effect works on irregular shaped asteroids. Again, these are illuminated by sunlight. They remit the radiation, and the remitted radiation can produce a net torque that changes the obliquity and changes also the spin rate. What is interesting is that if you consider an ensemble of random shapes, maybe random Gaussian spheroids or other potentially distribution can represent real asteroids, then you find that YORP has two regimes. It tends to align or anti-align the spin vector with the orbital vector. The YORP effect tends to produce obliquities near 0 or 180. So if you have random distribution of obliquities at the beginning, as you expect from a collision, then YORP will be pushing the obliquities closer to 0 or closer to 100. And this is exactly what we think is happening in this region. These distributions started basically random, but over time, the YORP turns out to be extremely sensitive to the asteroid size, and it's especially efficient for very small bodies. So over time, YORP has been pushing obliquities to the sides. So when we recover these obliquities, they are some sort of mean obliquities over the family age, and tells you that the YORP has already modified this distribution. So in a sense, these results are a detection, observational detection of both the Yarkovsky effect and the YORP effect for a population of asteroids, which has not been done before. Now we can ask a question, what are the effects of the radiation effects on much longer time scales than 10 million years, right? On hundreds of million years. To illustrate that, I have created a family here. I think maybe 1,000 fragments there. And I plotted in a interesting space. This is the semi-major axis. I have given the family some ejection speeds of the order of 50 meters per second. So that's the spread you see here. And assume that the absolute magnitude are between 12 and 18. For 10% albedo, it maps between 1 kilometer and 17 kilometers. And just for this example to be somewhat realistic, I also have the largest fragment, which is sitting here. So what happens on tens of millions of years after breakup? One important assumption I made is that I assume that the obliquities are randomly distributed, like in that initial state where fragments fly into space and you don't expect any concentration anywhere there. And also I ignored the YORP effect. So this is just what would happen for a fictitious family over 200 million years. So as you can see, it would spread because of the Yarkovsky effect is affecting smaller bodies more than the large ones. The spreading is more significant in small sizes. What is interesting on this is that the envelope here links to family age, right? In this case, the envelope is, semi-major axis of the envelope minus the center. The center is maybe centered on the largest fragment. Is this function of the absolute magnitude? This scaling comes simply when you take the 1/d dependence of the Yarkovsky force, where d is the diameter, and you map it to absolute magnitudes. So smaller bodies will be drifting more, and you expect this dependence. But this coefficient here depends on the age, right? So if you have older family, it will be spread much more. If you have younger family, it will be spread much less. So this offers a simple method how to estimate the ages of families that are even hundreds of millions or billions of years old. Just fit an envelope to it, and from these coefficients, just map it into the age. This method has been applied, but it turns out it's a simple method that has some drawbacks. One of the drawbacks is that this method ignores the initial ejection velocities of the fragments. In fact, this envelope should be a combination of the initial velocities of the fragments, which change semi-major axis somehow, and then the Yarkovsky spreading over the family age. And if you just fit an envelope, interpret it as the Yarkovsky spreading, you ignore the contribution of the ejection velocity field. So in this sense, this method can give you only an upper bound on the family. If you ignore ejection speeds, you just get an upper bound. So it's an approximate method how to get age of the family. This has also been applied in the past in many cases. This is a case of the Themis family. If the family is billions of years old, the contribution of the ejection velocity field is insignificant because of the Yarkovsky effect have spread the family much more than the initial spread, right? So for these old families, the determination of age from the V-shaped envelope is pretty good. But if you go to families that are only a few hundred million years old, like the Massalia family, then really you have to consider this age as a maximum possible age for the family. And in all likelihood, the age of the Massalia family is younger than 300 million years, maybe 200 million years, maybe even younger. Okay, so now let's take the next step. I ignored the YORP effect, right, in the simulation. But we know that the YORP effect is real and should be affecting the obliquities, and that will map on how much each object will drift by the Yarkovsky effect, because the Yarkovsky effect depends on obliquities. So here's the same case as before, but now accounting for the YORP effect. I didn't actually account for the YORP effect. I just assumed that the obliquities are near zero or near 180 degrees, as if the YORP effect would be instantaneous, and just to do the extreme case, which is easy to understand. So this is what happens when you account for the YORP effect, and as you expect, you move the bodies at maximum rate to the left or to the right, and this kind of creates this bunny ears that are there. And so that you remember it really well, I have an actual bunny here. This offers an even better method in understanding the family ages. Because of now, let's forget the envelope. The envelope is some combination of the ejection velocities and the evolution. So it's hard to how to break the degeneracy and understand which one is which. But instead, you can try to model the whole distribution, right? Including the Yarkovsky and YORP effects. And that's much more precise, much more accurate method for dating the families, because of you really reproduce all the details of the family. And this is an example of this being done to the Erigone family. This is the best fit in terms of the ejection speeds and the age of the family. So you can see that in this case, you would get probably the age of something like, from the V-shaped envelope, you would get something like 500 million years, but when you do this fitting, you find that the family is something between 300 and 400 million years old, and the ejection speed in case were something between 15 to 35 meters, right? So this is much better method for understanding the family ages. This comes from a work now almost 12 years ago, so this plot would need to be updated, but it shows the distribution of the formation ages of the old families. So each number stands for one family. So 158 is Coronis, 170 is Veritas, and so on, and these crosses are also families. This is the distribution, age on the x-axis and the parent body size on the y-axis. So the most interesting thing on this plot is, well, maybe for the large parent bodies, this is the distribution you should expect, right? The asteroid belt was slightly more massive at the beginning, so you expect many more collisions at the beginning and maybe just a few later on. But what is weird here is that you have lots of families in this region, younger than 2 billion years, with parent bodies less than 100 kilometers, but you don't have any in this region. So it's not very clear what's happening in this place. Maybe one should first redo this plot with the new catalogs to see if this still holds. And then there are different possibilities. Maybe if the parent body is relatively small, it produces small fragments, and the small fragments collisionally evolve, they spread by Yarkovsky, so maybe it's difficult to identify these relatively small families, but it's not very clear what's happening here and why the sample is incomplete, or whether it tells you something interesting. So in the last 10 minutes of this presentation, I would like to briefly talk about the asteroid families as sources of meteorites. And I will focus on L-chondrites, because of the L-chondrites represent 46% of meteorite falls, which is by far, which is more than any other meteorite type. As an example of L-chondrite, these are undifferentiated meteorites having chondrules. The L stands for the metallic iron content. It's not as high as for the H chondrites, but not as low as the LL chondrites. The interesting thing for L chondrites is many of them, roughly maybe half of them, or almost half of them, have clear signs of being heavily shocked. And this indicates that they were produced in a catastrophic disruption of a relatively large parent body, maybe 200 kilometers across, although we can debate this, what the actual size is. So if that's the case, then maybe you suspect that the source of L-chondrites is some of the collision families we discussed, right? Because they frequently result in disruption of very large parent bodies, produce lots of fragments. Those fragments may be meter size, they drift by the Yarkovsky force, and then later fall on the Earth. So that's a good question. Do L-chondrites come from the same family? And if so, which family it is? Another clue to which family it could be is that the radioscopic dating of the shock determines that the breakup happened roughly 470 million years ago. And there is some high precision dating that indicates that the error bar, very low error bar. So if we take this for real, we should be looking for a relatively large family with the age roughly 500 million years. And the question if the parent family of the alconorites can be identified. Now, an important constraint on that comes from telescopic observation, spectral observation. So this is a comparison of, let me step back. In the telescopic observation, you see the spectrum, right? And in the spectrum, you see some absorption bands, like typically at 1 micron, 2 micron. And these absorption bands are linked to how much olivine and pyroxene you have on the asteroid surface. And if you do things carefully, you account for space weathering and stuff like that, then you hope to find what the olivine to pyroxene ratio is for that specific asteroid you look at. And people look at specific asteroids in specific families, clump them together, Gefion, Massalia, Coronis, and these histograms show the distribution. Once you have that, you can compare that to lab spectra of different types of chondrites, H chondrites, L chondrites, LL chondrites. These distributions are overlapping and pretty large, so there is a significant uncertainty in mapping the lab spectra into the families. But maybe if you consider this list, and this list is actually much longer, I just cut it so that it's not confusing, maybe you can convince yourself that maybe Agnia, Merxia, Myophocia are not good proxies for the alchondrites, but maybe something like Massalia or maybe Gefion as well are spectroscopically good matches for the alchondrites. If you go down, these histogram shifts to the right, to the LL chondrites, and you don't get good matches. So maybe somewhere in this region, Massalia and Gefion could be plausible sources of the alchondrites. So let's just discuss that. Let's focus on these two families and compare them. So Massalia family is this large family in the inner main belt. Being in the inner main belt is significant because of it is much easier for bodies in the inner main belt to evolve on Earth crossing orbit, maybe by drifting by Yarkovsky to the left and hitting the nu-6 resonance, or maybe drifting to the right, hitting the 3-to-1 resonance, which is unstable, and shoots the asteroids in the NEO space, or the meteoroids in the NEO space. So Massalia is potentially a larger source of meteorites just because of its location in the main belt. Gefion, on the other hand, is located in the outer part of the main belt, so it is more difficult for these bodies to drift to the NEO space and impact on the Earth. So Massalia here wins on the efficiency. Massalia has an inconvenient age. If you apply the Yarkovsky YORP dating for Massalia, you find, unless you find that the family is about 200 million years old, maybe with a 50% uncertainty. So it seems inconsistent with 500 million years. Gefion, on the other hand, has age that's better aligned with the age inferred from the shock ages of alchondrites. If you just apply simply the V-shape method to Gefion, you would infer it is billion of year old, and people have done it in the past, but you need to account for the ejection velocity field, which is done, and when you do, you find it's much younger. Gefion was one of the most super catastrophic breakups in the main belt, meaning that the fragment that survived is less than 1% of the parent body mass. So it was really big breakup, Gefion, the most catastrophic breakup that happened. So what can we do more, right? Massalia wins on the efficiency. Gefion perhaps has a more plausible age. So let's see how meteorites evolve from these families. Okay, So this is the position of the Massalia-Jeffian families in the main belt. This is the Earth crossing. So when anybody from the Massalia reaches this space, it can impact on the Earth, can become meteorite. And the same thing for Jeffian. So just to illustrate this, I have taken 1 meter size bodies. I assigned them the Yarkovsky drift, I assigned them random obliquities, and let them evolve over time to see how these small objects reach the Earth crossing orbit. And of course they are small, so they will be drifting much faster than the kilometer size. They will be drifting by the Yarkovsky force, but much, much, much faster. So this is what happens for the Massalia meteoroids. Well, some evolved to the left, some evolved to the right, hitting the resonances and evolving to a place where they can impact. The red symbols are the actual bodies, and I just plot the black symbol just to see how they populate the whole space. And the same can be done for Jeffian. The efficiency for Jeffian is slightly lower, and it takes longer time for the meteoroids to reach the crossing space, which is the question of efficiency that I already mentioned. So this is the final distribution after 200 million years, which we think is the age of the Massalia family, and after 470 million years, which would be aligned with the shock ages of the chondrites, and you can see these distributions, right? Which is not very quantitative. You want to be quantitative. And to be quantitative, you can bin this distribution to a sort of a map that shows where these meteorites spend most of the time, and when you multiply that map by the collision probability of the Earth, you will infer where most meteorites from the Massalia family should be impacting from, and the same thing for Jeffian. And these are the maps that you can produce. And this is the map in semi-major axis eccentricity. The red area is where you expect most of the chondrites coming, if they are coming from the Massalia family. And the black dots here are about 20 chondrites for which we have the actual orbits. So these chondrites were observed during the fall through the atmosphere, and people from that trajectory, if seen from different directions, are able to infer what the pre-atmospheric orbit of that body was. And then you recover it on the Earth, on the surface, you analyze it in lab, you realize it's an chondrite, and you make this catalog of a couple of dozens of chondrites with measured orbits. So this is the map from Massalia, this is from Jeffian, and it's not particularly diagnostic in this case, right? We would need much bigger statistics to be able to compare these maps in more detail. Perhaps slightly more diagnostic is the distribution in the inclination. I actually think that the Massalia family is fitting this wedge-like distribution better than the Jeffian family, which is missing some bodies at the bottom, but you know, it's not quantitative enough to be sure whichever is the case, and hopefully in the future, when the statistics improves, one could make quantitative tests of these two families or even other families as a source of chondrites. So these are the key points to remember. Proper elements help to identify fragments. They are constant of motion, and therefore they remain constant over billions of years, so you can use them to identify ancient disruptions. Today we know 360 collisional families, and they provide useful constraints on physics of large-scale collisions, the lack of asteroid differentiation, space weathering, and other effects. Carine and many more asteroid families, currently 105, have age less than 10 million years, and they are dated based on the convergence of the angles. The Yarkovsky YORP-based chronology helps to constrain ages of the old families, and altogether these families represent important constraints on the collisional evolution of asteroids. Compositionally, Massalia and Jeffian families are plausible sources of chondrites. Massalia is better placed, but has inconvenient age. So this was for today. a week from now, I will be talking about the dynamical origins and properties of near-Earth asteroids. So, well, I hope to see you next Thursday. Thank you.